Today I'm going to introduce to you sequences and series. Let's start with sequences. A sequence is basically just an ordered list of numbers. For example, a sub 1, a sub 2, a sub 3, all the way up to a sub n. Usually the subscripts are used so we know which term in the sequence we're talking about. For example, a sub 5 means it's the fifth term in the sequence. And this is referred to as a finite sequence because it doesn't go on forever. It has a finite number of terms. On the other hand, if I just had a sub 1, a sub 2, a sub 3, ... and nothing at the end, then that would be an infinite sequence. And so two totally different types of sequences, and you'll find different applications of those in mathematics. Every once in a while you'll see some textbooks, they'll have the first term designated as a sub 0. So then in that case, a sub 5 would actually represent the sixth term. So you have to be aware of how it's designating the first term. But usually a sub 1 is the way we go. Alright, so let's look at some examples. What if I ask you to compute the first three terms of this sequence? Now notice this sequence has a definition for it. It's defined explicitly. A sub n is going to equal -1 to the nth power times 2n for all n that are greater than or equal to 1. So what we're going to do is we're going to say, okay, let's start with n equals 1. That's going to be a sub 1, our first term, and so we're just going to plug in 1 for all the n's. And so when we simplify that, we get -2. And then we'll let n equal 2. And that'll define a sub 2. And we'll plug in 2 for all the n's, so we get -1 squared times 2 times 2. And so we're going to get positive 4. Maybe I'll write it over here. Alright, and then finally this said the first three terms. I'm running out of space. So then I'm going to say n equals 3, and that'll define a sub 3, the third term. And that's -1 to the third, which will be -1, times 2 times 3, which is 6, so we'll get -6. So the first three terms are -2, positive 4, -6. And you notice it has a nice pattern there. We're multiplying by -2 each time to get to the next value. And that's basically what this definition is telling us. Find the 12th term for a sub n is equal to that expression. Right? Same idea. To find a sub 12, that means that n is equal to 12. So we'll just plug in 12 for all the n's, and we get 2 plus -1 to the 12th, which will be a positive 1, over 12. So that's going to give us 2 plus 1 is 3 over 12, or 1/4. And that's it. Pretty simple. Alright, now, sometimes instead of sequences being defined explicitly, we have recursive sequences. And those types of sequences use a previous term or previous terms, plural, to define what the next term is. So each term is defined based on the term or several terms that came before it. So let me show you an example. Compute the first 5 terms. So this is a recursively defined sequence, because if you notice, the n plus second term is equal to the nth term plus the n plus first term. Now what that means is basically that the next term is going to equal the 2 previous terms added together. So we have to start somewhere. We need to know what the first term is. So they tell us the first term is 1. And the second term is also 1. So now we'll have to find the rest of them. So when n is 1, a sub 1 is equal to 1. When n is equal to 2, a sub 2 equals 1. That was defined for us. They gave those to us. Now we're ready to do some computations. When n is 3, a sub 3 is going to equal, now I'm using this definition. So, and here's where sometimes students get confused. So what I'm going to do is get rid of these and look at this definition, and a sub n plus 2. If I'm doing a sub 3, then that's really saying that n plus 2 is equal to 3. So I'm going to plug in 1 for all the n's. So that means a sub 3 is going to equal a sub 1 plus a sub 2. That's why I described this when I first showed this to you as, think of what it's telling you. The n plus second term is equal to the nth term plus the n plus first term. So we're adding the two previous terms to get the next term. So the first term was 1, the second term was 1, so that's going to give us 2. So a sub 3 is equal to 2. How about a sub 4? A sub 4. Well, using this definition, I'm going to have to plug in a 2 for n, because n plus 2 now is equal to 4, this 4 right here. So n is going to be 2. So I'm going to plug in 2. So a sub 4 is going to equal a sub 2 plus a sub 2 plus 1, which is 3. Or in other words, the second and the third added together. Well, the second term was 1. The third term I just figured out. That was a 2. So 1 plus 2 is 3. And finally, a sub 4, a sub 5 is going to equal a sub 3 plus a sub 4. And the third term was a 2, and the fourth term we just figured out was a 3, and so we get 5. Now, that may seem confusing at first, but let's go back to that definition. And so what it's saying is the n plus second term is equal to the nth term plus the n plus first term. If I'm listing out sequences, I got the first one, the second one, the third one, and actually I'll use a's to make it easier for you. I have a sub 1, a sub 2, a sub 3, and dot dot dot. And then I get down, eventually I'll have a sub n. What's the next one after that? Well, a sub n plus 1. What's the next one after that? A sub n plus 1, which would be n plus 2, etc. So in this definition, it's saying the second term, the n plus second term is equal to the nth term plus the n plus first. So to find any term, you just add the 2 before it. So I probably wouldn't have done all this work that I showed you in red and green. I just would have started with the first term is 1, the second term is 1, the next one is adding those 2 together, the next one is adding 2 plus 1, the 2 before it, then I add the 2 before the next one, 2 plus 3 is 5, and so on. And if I keep going, 1 plus 2 is 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34. You get the idea. This is actually a very famous sequence, and it's called, got it here somewhere, there it is. It's called the Fibonacci sequence. And some people do their IBIAs on this, and it's a sequence that shows up in nature quite extraordinarily. Alright, so that's a recursive sequence. So we have explicitly defined, the first few examples, and now we're recursively defined. Alright, so those are the basics of sequences. Now, a series is when you add up all the terms in a sequence. So for example, this is a series. 1, 3, 5, 7. You see the pattern, they're just odd numbers. 9, 11, 13, 15, 17, and 19. That's a sequence. That's a sequence, a bunch of numbers separated by commas. This is a series, when you add up the numbers in a sequence. Alright, so then if we just add all these numbers together, what are we going to get? Well, we could grab a calculator, or we could use our brains a little bit and say, you know what, instead of adding 1 to 3 and then 3 to 5, what if I match them up this way? 1 plus 19 is 20, 3 plus 17 is another 20, 5 and 15 is another 20, 7 and 13 is a 20, 9 and 11 is a 20. How many 20s do I have? 1, 2, 3, 4, 5 20s? So that should be equal to 100. Okay. All right, now representing a series, we like to use sigma notation. It's a notation in mathematics that tells us that we're dealing with a series. And we use a Greek letter sigma. And so whenever you see that, you should think, oh, this is representing a series. We're going to be adding up a whole bunch of terms or a whole bunch of numbers. So let's look at an example. Now, how would you read this? There's a couple different ways to say it, but basically you would say sigma k equals 1 to 4 of 2k minus 1 quantity squared. So now, this is our index here. K is our index variable. This is the lower limit, and this is the upper limit. So that means that k is going to start at 1. You always have to go by integer values. So k will be 1, then k will be 2, and then k will be 3, and then k will be 4, and then we stop, because up here it says stop after 4. So those numbers could be anything, and it has to be, you can't have a bigger number on the bottom, that wouldn't make sense. So what we're going to do is we're going to evaluate this expression, first when k equals 1, so 2 times 1 minus 1 squared. Then we're going to evaluate when k is 2, so 2 times 2 minus 1 squared. Then we'll evaluate when k is 3, 2 times 3 minus 1 squared. And finally when k is equal to 4, 2 times 4 minus 1 squared. Okay, and then we're going to add all of these together. So this is going to be 1 plus 3 squared is 9, plus 5 squared is 25, plus 7 squared is 49. So that's going to give us 10, that's going to give us 50, 75, 84. So this expression, this sigma expression, equals 84. And that's it. It's not really that difficult. It's just the first time you see it, it might look a little strange, but it really is pretty straightforward. The tougher part is if I give you a pattern, a series, and ask you to write sigma notation for that. For example, write sigma notation for this. So what you want to do is you want to look for a pattern where numbers are increasing by ones, because that's what the sigma index represents. And if I think of this as 1x to the first power, I see a pattern here. I see that the coefficient keeps increasing by 1. It starts at 1 and it ends at 6. And the exponent is also the same as that coefficient. So I want my index variable to represent both the coefficient and the exponent. And then the x is just part of my expression. So there's a couple ways to do it. I would say this is probably the most straightforward way. And say, okay, let's say n equals 1 to 6 of n times x to the n. So we're going to plug in 1 for n, and we get 1x to the first. The sigma says that we're adding all these together, so we get 1x to the first, plus, and then n bumps up to 2, so we get 2x squared, plus, and then n bumps up to 3, and then to 4, and then to 5, and then to 6. Now, I use letter n here. Somebody else might say, well, I want to use letter k. And notice it's pretty much exactly the same thing, except we're using k instead of n. Somebody else could use j or I or whatever they wanted. Okay, you have your choice. Now, there's even more ways to write it than just this. For example, let's go to this one. Here's a more complicated way to work it out. Instead of having my index go from 1 to 6, what if I made it go from 2 to 7, but then I just made this k minus 1 and this k minus 1. So I'm starting at 2, and when I plug 2 in here, I get 2 minus 1 is 1, and I get 1 here, and so that's what I want. And then when I plug in 3 for k, k minus 1 becomes 2, and finally when I get to the 7, it becomes 6x to the 6th. So I still get the same answer. It's just a more complicated. Why would somebody write it that way? I don't know why. But sometimes you'll see expressions that are more complicated, and it might help to think of them as a little simpler. I also came up with a couple more crazy ones to show you just how it works. So if we look at the blue one, when this says j starts at 0, if I plug in 0 for the j's, I'm going to get 1x to the first, and then j bumps up to the next number, which would be 1. I plug in 1 for j, I get 2x to the second. Then j bumps up to 2, then it's going to give me 3x to the third. And then it goes to 4, and that's, 3, and then that's going to give me 4x to the fourth. Then j is going to bump up to 4, and I'm going to get 5x to the fifth. And finally, j is going to equal 5, and that'll give me 6x to the sixth, and I stop. And that's the same series that I had to start with. And if you notice the purple one, that also will work. You start at 101, this evaluates then to 1x to the first power. When you check the last one, 106, this evaluates to 6x to the sixth power. So there's an infinite number of ways you can write a sigma for a particular series. So when you have a problem that says rewrite using sigma, go with the simplest one. Don't make it more complicated than it needs to be. All right, there's the properties of sums, which are represented with sigmas. So the green one actually is a little more straightforward, and it says if you have a constant times some expression, you can pull the constant out in front of the sigma, evaluate the sigma first, and then multiply that answer times the constant. One that sometimes confuses students is the purple one here, and it says sigma k equals 1 to n of c. Well, if c is a constant, then that says, okay, when k is 1, we plug in 1 for k. There's no k in this expression, so it's just going to be c. And then k bumps up to 2. And then we there's no k to plug it in, so it's just c again when k is 2. And then when k is 3, it's just c again. And then when k is 4, and 5, and 6, and 7, and when k is n. Well, how many c's do we have? We have n c's, because we went from 1 to n, so it's just going to equal c times n. And then one of the last properties that sometimes is useful is if we're doing sigma and we're adding or subtracting two expressions, you can do each expression individually and then add or subtract those two answers. One more thing that deals with series are called partial sums. And if you want the sum of the first n terms of a sequence, it's called the nth partial sum of the sequence. So remember, the sequence is just a list of numbers. The series is when you are adding those numbers up. If I want to add up just the first n number of terms in a sequence, that's called a partial sum. So I'll show you an example of that. Let's say we want the fourth partial sum of this series. Now notice, this series goes from 1 to infinity. So it's an infinite series. It goes on forever and ever and ever and ever. So we want the fourth partial sum. So that just means we want the first 4 terms. So what are we doing? We're starting at 1. So let's plug in 1. We're going to get 3 times negative 1/2 to the first power. Plus, we're summing these up, then n bumps up to 2. So we plug in 2 for n. 3 times negative 1/2 to the second power. Plus, then n bumps up to 3. So we plug in 3 for n. So we have 3 times negative 1/2 to the third. And then n bumps up to 4. And we have 3 times negative 1/2. And we plug in 4 for n there. So those are the first 4 terms, so this will give us the fourth partial sum. And then we can go ahead and simplify this. So I have negative 3/2 plus 3/4 minus 3/8 plus 3/16. And then I'd have to get a common denominator. So that would be 16. So I'm going to have to multiply the first fraction by 8 over 8. So I'm going to have negative 24. And then the second fraction I'll have to multiply by 4 over 4. So I'll have plus 12. And then the third fraction I'll have to multiply by 2 over 2. So I'll get minus 6. And then the last fraction I'll have to multiply by anything. So we get a negative 12, negative 18, negative 15 over 16 is our final answer. And so that's the fourth partial sum of this series. 4? No, we're not in a golf course, we're in a math class. So if you haven't seen that symbol before, it means factorial. Factorial. And so 4 factorial means we're going to multiply all the integers from 1 up to 4 and then get our answer, which is going to be 24. Okay, so in general, if n's a positive integer, n factorial is defined as 1 times 2 times 3 times 4 all the way up to n. Now I tend to write it backwards like I did in the 4 factorial example. You'll see why if you do some work with probability, it makes more sense to write them with the biggest number first when you're counting. But it doesn't matter either way, because we're multiplying, and of course multiplication is commutative. Alright, so let's do a couple more examples with factorial so you can get comfortable with it. Alright, what if I ask you to simplify 8 factorial over... Oops, I shade one away. 8 factorial over 5 factorial times 3 factorial. Alright, so let's write out what's 8 factorial. It's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by, what's 5 factorial? 5 times 4 times 3 times 2 times 1. And then times 3 factorial, 3 times 2 times 1. Now, there's no need to multiply all this stuff out and then try and divide these gigantic numbers. We can do some canceling. Because everything's being multiplied, well, this 5, and this 4, and this 3, and this 2, and the 1, which doesn't really matter. Those all cancel and become 1s. And then 3 times 2 on the bottom is 6, so I can cross that out with the 6 on the top. So all I'm left with is 8 times 7 on top and 1 on the bottom. So all of that simplifies to 56. No calculator needed. Now calculators do have a factorial button, so that does come in useful on your graphing calculator, but we didn't really need it for that. And it's important to be able to do this without a calculator, because then we get to the next expression. Go ahead and try and simplify this. You might want to even hit pause, give it a shot, and then hit play again. Alright, x plus 1 factorial. That means x plus 1. What comes right before that? Well, just x. What comes before that? X minus 1. What comes before that? X minus 2. X minus 3. All the way down to 1. If you want to write it the other way, start with 1, that's fine. Maybe I'll write that again in a minute. Alright, on the bottom, x, and then x minus 1 factorial. Factorial is treated like an exponent. So we want to do the x minus 1 factorial first and then multiply by this x out here. So it's not everything factorial. It's the x minus 1 that's factorial. So we have x minus 1. What comes before that? X minus 2. What comes before that? X minus 3, etc. all the way down to 1. And then we also multiply all that by an x in front. And so there you go. Now, what can we cancel? Well, if you look closely, x minus 1, x minus 2, x minus 3, all this stuff will cancel down to 1. And then this x cancels with that x. So all that simplifies down to just x plus 1. It takes a little while to get used to, but once you understand that concept, it isn't really that difficult at all. What if I ask you to expand 2n factorial? Now once again, this factorial only goes with the n, not with the 2. If I wanted it to go with the 2, I would have written parentheses 2n factorial. And in that case, it would be 2n, and then 2n minus 1, and then 2n minus 2, 2n minus 3, keep going until you get to 1. But for this case, we have a 2, and then we're going to do n factorial, which is n, and then 1 less than that, and then 1 less than that, and 1 less than that, all the way down to 1. So that is what 2n factorial equals. Alright, so here's your problem set, page 577.